Welcome to today's video, which covers variation of parameters. Before we jump in, I want to review what we've done before this point. We started by solving homogeneous linear differential equations. So we found our auxiliary or characteristic equation and solved for the roots, which we then used to find the general solution. Next thing we did is we solved the non-homogeneous equations. And so we started by solving the homogeneous again. And then in the last video, we learned the annihilator approach, or the method of undetermined coefficients, which we used to find the particular solution. So one thing we talked about, though, is that the annihilator approach only works if our equation is set equal to some function that we know how to annihilate. What happens if we have a function, though, that we don't know how to annihilate? So that's where this new method comes in, which is called the variation of parameters. So we're going to start by revisiting a first-order equation. So this equation that we have right here, we notice that it's non-homogeneous. If it's non-homogeneous, our general solution is going to be the sum of the characteristic and the particular solutions. So our characteristic solution is C1 e to the negative integral of p of x dx. The particular solution, we haven't found a general solution for this yet, but I'm going to tell you what it is. So it ends up being e to the negative integral of p of x dx. And then you have the integral of e of the integral of p of x dx times f of x dx. So we're going to derive that in a minute, but that's what we're going to end up finding. And so what we notice is this right here is the characteristic solution, or the characteristic equation. So what this shows us is that y of p is sort of, real technical term there, sort of a multiple of our characteristic equation. Now, why is that the case? Well, let's go through and derive this. So we're going to use reduction of order. So our equation is y prime add p of x times y is equal to f of x. And we know our first solution is that c1 e to the negative integral of p of x dx. So we want to find y of p, which is going to be u1 times y1. So that's just from the reduction of order process. And so if we use that equation, we know that we're going to need the first derivative. So our y of p prime is u prime y1 add u1 y1 prime. So then if we substitute that, both of these, back into our initial equation, what we're going to end up with is u1 prime y1 add u1 y1 prime add p times u1 y1, which is equal to f of x. So we're going to do a little bit of factoring here. We notice that we have some terms that have a u1. So if I factor that out, I get y1 prime add p times y1. And then I have one term that has a u1 prime, which is multiplied by y1. Now, if you remember, initially we solve our homogeneous equation. So this is the original equation. And if it's homogeneous, that's going to equal 0. So what that gives us then is that u1 prime y1 is equal to f of x. So of course, we're going to integrate. And I'm going to continue up there. So I get u1 prime is equal to f of x over y1. I'm going to integrate. So I get u1 is the integral of f of x over y1. Now, I want to remind us that u is a function of x. So this is really u1 of x. Just want to recall that. So now that we have that u, we can go back and find our y of p. So our y of p, if we recall, is u1 y1. So our y of p then ends up being y1 times the integral of f of x over y1. And if you're going to notice, this is exactly the same as this y1 above. It's just written in a different form. Not y1, yp. So this y of p is exactly the same as the y of p that we wrote above. So what we're going to do now is we're going to do a very similar process, but we're going to look at a second order equation. So first thing that I want to point out with our second order equation is that we have a lead coefficient of 1. So we have a lead coefficient of 1. We also are going to know that we have y1 and y2 that are solutions. Right, and how do we find this? Well, first thing that we would do is we would make our equation homogeneous, and then its second order, which would give us 2 solutions. So these 2 solutions would form our complementary solution. And then because it's non-homogeneous, we're looking for the particular solution. So we're going through the same process or a similar one to what we did above to find our particular solution. So our particular solution, y of p, by superposition is going to be of the form u1, y1, add u2, y2. Again, this is by superposition. Keeping in mind that u and y are both functions of x, right? So our goal is to find y of p. So we're going to need first derivative and second derivative. So if I go to find y of p prime, I'm going to get u1 prime, y1, add u1, y1 prime, add y2 prime, y2, add u2, y2 prime. Okay, so we're going to switch this around a little bit. So I'm going to keep u1, y1 prime and u2, y2 prime out in front. And then in the back, I'm going to have u1 prime, y1, add u2 prime, y2. Now, to solve this, we are going to impose a condition. We are going to require that the sum of those 2 terms is equal to 0. We are going to require that, and I'm just going to star this because we are going to use that requirement later. So now, second order, I'm going to need my second derivative as well. So I'm just using this part now since I'm requiring that those last 2 terms are, the sum is equal to 0. So I get u1 prime, y1 prime, add u1, y1 double prime, add u2 prime, y2 prime, add u2, y2 double prime. So now that we have all of that, of course what we're going to do is we're going to go back to our differential equation. Our differential equation being that y of p double prime, add p times y of p prime, add q times y of p. So we're going to have a lot of terms here. I didn't give myself a ton of space, but we end up with u1 prime, y1 prime, add u1, y1 double prime, add u2 prime, y2 prime, add u2, y2 double prime. Then I have p times u1, y1 prime, and I have p times u2, y2 prime. And then I have q times u1, y1, and q times u2, y2. Whew. Okay, whole lot going on here. So of course what you can probably recognize is that we're going to have to factor this. So we're going to have to do a little bit of factoring. First, I have some terms that have a u1. And when I find those terms that have a u1, so going above, that would be this term that has a u1, this term that has a u1, and this term that has a u1. So that would give me y1 double prime, add p times y1 prime, add q times y1. Then I also have some terms that have this u2. So if I go and find those terms that have u2, I have this term, and this term. So that gives me y2 double prime, add p of y2 prime, add q of y2. And then if I find those terms that I have left, the terms that I have left are u1 prime, y1 prime, add u2 prime, y2 prime, and all of that is equal to f of x, right? So this is equal to f of x also. Okay, so thinking about what we know here. Well, we know that y1 and y2 are solutions to the homogeneous equation. So therefore, this sum right here and this sum right here are both equal to 0. So really, this is all that we have left. Okay, so we have 2 conditions right now, or we have 2 equations. we have this equation right here, and we have this condition that we imposed where we said that sum was going to be equal to 0. So those two equations together are going to give us a system. I gave us more room on the next page to keep going with this process. So those two equations give us the system y1 u1 prime, add y2 u2 prime is equal to 0, and then y1 prime u1 prime, add y2 prime u2 prime is equal to f of x. So this is our 2x2 system. Now, we need to remember that we know y1 and y2, we need u1 prime and u2 prime. Okay, so then this is going to go back to something that we did a few sections ago. I can't remember quite how many, but we used Kramer's rule to solve systems. So what we get then is u1 prime in the denominator is the determinant of the matrix that has all of the coefficients. So all of these coefficients. So that's going to be y1, y2, y1 prime, y2 prime. And then in our numerator, what we do, if we're solving for u1 prime, we are going to take the answer and put it in place of that first column. So what we do is we have 0, we have 0 and f of x, and then just y2 and y2 prime. Likewise, our u2 prime, denominator is going to be the same, so y1, y2, y1 prime, y2 prime. This time, the 0 and the f of x go in the second column, and the first column is just y1 and y1 prime. Okay, so solving for this, it would give me u1 prime and u2 prime, which I could then use to find the particular solution. A little bit of notation. We normally call this bottom matrix W, and we're going to call this first one W1 because it relates to U1, and this one W2 because it relates to U2. Okay, so that is the general process. Now we are going to do some examples to see what this looks like. Here is the summary of what we just talked about. Okay, so first thing, you're going to have an equation that is non-homogeneous, and as a reminder, it's going to need to have a lead coefficient of 1. We're going to use that to find the complementary solution. So remember, that comes from the homogeneous equation, the one where we're set equal to 0. Then what we're going to do is we're going to find the Wronskian. So the Wronskian would be y1, y2, y1 prime, y2 prime. Then we'll find w1 and w2. w1 would be 0 and f of x, and then y2 and y2 prime. w2 is going to be y1, y1 prime, and then 0 and f of x. And then we're going to find u1 and u2 by integration. So u1 would be w1 over w, likewise for u2. So our particular solution then would be u1 y1 add u2 y2. And finally, we would use that for the general solution, which would be the sum of the complementary and the particular solutions. So now that we've gone through this whole process, let's take a look at an actual example. So here's our first example. Solve this equation. So we notice that it is non-homogeneous because we're not set equal to 0. So let's talk about first, would we be able to use annihilation here? The annihilator method. Well, can we annihilate x plus 1 times e to the 2x? Yes. We would have to use d subtract 2 quantity squared. D subtract 2 because of this 2, and then this x plus 1 tells us that that root happened twice. So we could use annihilation if we wanted to. We're not going to because we're going to practice this new method that we now have. So we're going to start with our auxiliary equation. So that's our m squared, subtract 4m, add 4 is equal to 0. So we have m subtract 2 squared is equal to 0 then. So we have roots of 2 and 2. So this gives us our characteristic solution. which is going to be c1e to the 2x, add c2x e to the 2x. So e to the 2x then is our first solution. X e to the 2x is our second solution. So next thing that we're going to do is we're going to find the Wronskian. So first solution is e to the 2x, and then we have x e to the 2x. And then we're going to need the derivatives. So 2e to the 2x, and then 2x e to the 2x, add e to the 2x. So if I find the determinant here, I'm going to get 2x e to the 4x, add e to the 4x, subtract 2x e to the 4x. So w then just ends up being e to the 4x. Okay, so next thing that I'm going to do is I'm going to find w1. w1, I'm replacing that first column with 0 and my answer function, which is that x plus 1 e to the 2x. And then the second column stays x e to the 2x and 2x e to the 2x, add e to the 2x. Okay, so this is going to give me 0, subtract x multiplied by x plus 1 times e to the 4x. So that w1 just gives me negative x plus 1 e to the 4x. Okay, likewise, w2. This time the first column stays the same, so e to the 2x and 2e to the 2x, and I replace the second column. So w2 then ends up being x plus 1 e to the 4x. Okay, so next thing that we're going to do then is my u1 prime is going to be w1 divided by w. So that w1 is the negative x plus 1, e to the 4x. And I'm dividing that by e to the 4x. So my u1 prime ends up being negative x plus 1. So that's what I'm going to integrate then. So I'm going to integrate negative x squared subtract x dx. So I get u1 then is equal to negative 1/3 x to the 3rd, subtract 1/2 x squared. And remember, we're not concerned about the constants. So my u2 prime then is w2 divided by w, which is that x plus 1 e to the 4x over e to the 4x. So we get u2 prime then is equal to x plus 1, which I'm going to integrate. So the u2 then ends up being 1/2 x squared add x. Okay, so now if we recall, our particular solution is going to be u1 y1 add u2 y2. So our particular solution is going to be the negative 1/3 x to the 3rd, subtract 1/2 x squared times e to the 2x. And we're adding to that 1/2 x squared add x times x e to the 2x. And if we simplify, we're going to end up with 1/6 x to the 3rd, add 1/2 x squared times e to the 2x. And now finally, where that gets us is our general solution. Our general solution is going to be the sum of the complementary and the particular solutions. So our general solution is going to be c1 e to the 2x, add c2x e to the 2x, add 1/6 x to the 3rd, add 1/2 x squared e to the 2x. Now, if we had used annihilation instead, we would get the same answer. So that was the method variation of parameters. Let's take a look at one more example together. Okay, so here is our next example. First thing that I want us to notice is we have a 4 here. So the very first thing I'm going to do is I'm going to divide that 4 out. So I get y double prime add 9y is equal to 1/4 cosecant of 3x. Okay, so we should be asking ourselves, can we annihilate here? And this is one of those cases where we don't know how to annihilate cosecant of 3x. So this is a case where we could not use annihilation or the method of undetermined coefficients. We would have to use variation of parameters. So at this point, maybe you want to try this one on your own. I think that's a great idea. If you feel confident and comfortable, pause the video and try this one. If not, or you just don't feel like it, then stick with me. So our auxiliary equation is m squared add 9 is equal to 0. So our solutions end up being 0 plus or minus 3i. That gives us then an alpha value of 0 and a beta value of 3. So our complementary solution then is e to the 0x, c1 cosine of 3x, add c2 sine of 3x. Rewriting that, because we don't need that e, we get c1 cosine of 3x, add c2 sine of 3x. Okay, so our first solution, our y1, is cosine of 3x, and our second solution is sine of 3x. So let's use that to find the Wronskian. So we have cosine of 3x, and then we have negative 3 sine of 3x. We have sine of 3x, and 3 cosine of 3x. So that gives us 3 cosine squared of 3x, add 3 sine squared of 3x, which is just 3. If we find w1, we're going to replace that first column with 0 and cosecant of 3x. So then I have sine of 3x and 3 cosine of 3x. So that just ends up being, sorry, I forgot that 1/4. There's a 1/4 here. So that ends up being negative 1/4. And remember, there's a 1/4 because we need a lead coefficient of 1. Our w2, so we have cosine of 3x, negative 3 sine of 3x. We have 0 and 1/4 cosecant of 3x. So that ends up being cosine of 3x divided by 4 sine of 3x. And now we're ready to do some integrating. So our u1 prime is w1 over w, so negative 1/4 divided by 3. So our u1 prime is negative 1/12. When we integrate that with respect to x, we get u1 is equal to negative 1/12 x. Our u2 is going to be that cosine of 3x over 4 sine of 3x divided by 3. So our u2 prime. So our u2 prime, we're integrating cosine of 3x over 12 sine of 3x dx. So u2, integrating. So our u2 ends up being 1 over 36 natural log of sine of 3x. Okay, so our particular solution then is going to be our u1, u2, and then our two solutions. Okay, so that y of p then ends up being 1/12 x cosine of 3x, add 1 over 36 natural log of sine of 3x times sine of 3x. Okay, so all of that leads us to finally our general solution. So our general solution is c1 cosine of 3x, add c2 sine of 3x, subtract 1 over 12 x cosine of 3x, add 1 over 36 natural log of sine of 3x times sine of 3x. So I hope you took the opportunity to try that one on your own. If you did, I hope you did fairly well on it. Okay, that was our last example, but we do have a few other things to chat about. We can use this process for higher order equations. So a third order equation, for example, your W is going to be a 3x3 matrix. So we need to probably review how do you calculate the determinant of a 3x3 matrix. So let's say that we have A, B, C, D, E, F, G, H, I. and we want to find the determinant of this matrix. So what you're going to do is you're going to choose one row or column. So I'm going to start with A, and then what I'm going to do is I'm going to ignore the row and column that A is in, and I'm going to be left with the determinant of E, F, H, I. Then when I go on to B, the next one, I'm going to flip the sign, and then what I'm going to do is I'm going to ignore the row and column that B is in. So that would give me D, F, G, I. And then lastly, when I go to the third, I switch the sign again, and this time I'm going to ignore the row and column that C is in, which would give me D, E, G, H. So that would be how we find a 3x3 matrix. Now, what happens if instead we're looking at a matrix like A0E, B0F, and CDG? Okay, so we can choose any row or any column that we want. So on the first example, I chose the first row. Well, in this case, let's choose this column because I'm going to have 2 zeros. So here's what I need to know then. If I choose this column, if we remember, when we got to this B, we had to switch the sign. So we switch the sign, keep the sign, switch the sign. So what we would end up with then is we would have negative D, and then we're going to ignore the row and column that D is in. So we would get B, F, C, G, and that would give us our determinant. And again, that's just convenient because these 2 zeros means we're not going to have to consider 2 other determinants. So that was just a quick thing to review, and then one last thing to talk about. So one last trick, it's not really a trick, but let's say that this is our complementary solution and this is our particular solution. Well, if you notice, we have a term with x and we have another term with x. So our general solution then would be written as some constant of x, and then we have that c2x squared and that 3e to the x. So what we can do is, because both of these terms have an x in them, we can just write them together as one term. So if you see that in your homework, all we did was take those 2 terms and put them together. Okay, so thank you for watching. This was variation of parameters. Again, just another way to solve non-homogeneous equations. So until next time, thanks for being with me.